do not have 3D glasses but want to see Mars in 3D, you should come up and get some glasses, or raise your hand and we'll bring glasses to you. Our next speaker is going to be Margaret Landis, and she came from Northern Arizona University and is now a PhD candidate here at University of Arizona. And she is on the Dawn Science team, which is studying the asteroid Ceres right now. And she's also on the HiRISE Science team studying Mars, which is what she'll be talking about today. But feel free to subject her to questions about Ceres, right? Right? Okay, so without further ado, I will let Margaret take it away.
Thank you very much, Sarah, for the introduction. So I'm going to tell you guys a little bit this evening about my research and what it has to do with climate change on Mars and how we can learn more about climate change in general and especially on the Earth from it. So for future reference, the picture on the title slide right there is the South Polar Permanent Cap of Mars. It's mostly carbon dioxide, and we'll come back to that towards the end of the talk about why we care that it's there. But before that, let's go over a little bit of some climate change basics. So the greenhouse effect is something that affects terrestrial planets with carbon dioxide in their atmosphere, so it affects Earth and Mars. And so what happens here is we're going to, in the next couple slides, basically follow the life cycle of energy coming in from the sun and the Earth's atmosphere. So energy will come in from the sun, shown by this blue arrow, and hit the Earth's surface. And from there, some of it will be re-radiated back to space. But some of it will actually stay and heat up the Earth's atmosphere itself. So this is the part that you'll hear called colloquially trapped in the atmosphere, but it's not necessarily the case. And then there's also energy coming in from the sun that ends up heating up the Earth's atmosphere. And so the atmosphere is being heated, and so some of that energy, once again, is radiated back out of space, and some of it is radiated towards the Earth's surface. And the radiation that's causing the greenhouse effect that we really care about is indicated here by this red circle. So this is the energy that's going to be heating the surface of the Earth and heating the atmosphere, and kind of in a feedback cycle between those two regions. And this is what ends up largely controlling the temperature of the surface. And then another quick review, the carbon cycle is another important part of things, and this figure actually is an illustration of the carbon cycle is like on the Earth. So we have, in one case, carbon. This mic actually moves, I can move it, cool. So you have carbon coming in from the atmosphere that's being trapped in a biological cycle on the continents by being taken up by plants that's then fixed into soil in various ways. This is basically a carbon cycle driven by things living and dying and then decomposing. And that's kind of the same case on the ocean as well, except the carbon dioxide ends up dissolved in the ocean and then kind of goes through a similar cycle where biology is basically controlling how this carbon cycles. And then some carbon on the Earth ends up in rocks, which are then weathered, and then that carbon is re-released in the atmosphere. So for Mars, many of these things do not apply. Basically all the biology part, we don't know of any currently alive things on Mars, so that's gone. So that's probably not playing a major role in the carbon cycle of present day Mars. Which means that Mars's climate system is much more simplified than the Earth's. You don't have humans unburying liquefied dinosaurs and burning them. It's very straightforward. So what do we still have for Mars? One major way of trapping carbon dioxide, like I mentioned before, for the Earth is having that carbon dioxide trapped in rocks. And at some point in Mars's past, this happened. Other orbiting instruments that I'm not going to talk about as much in the rest of the talk, actually do spectroscopy. So what they can do is look for the fingerprints in light of different chemical compounds on Mars. And they have found rocks that basically form mostly from carbon and carbon dioxide sort of compounds, basically raining out of the atmosphere and solidifying on the planet. That's not necessarily to say that it ever rained on Mars, but that's kind of the point. Rocks can trap carbon dioxide. And so we know this happened on Mars. And the other way that you can have carbon dioxide come out of the atmosphere is actually can freeze out on Mars. Mars does get cold enough to have carbon dioxide freeze, and so this is why we have polar deposits, especially like the South Polar deposit here, which is a thumbnail of that title slide image. And from radar and other numerical modeling, we figured out that most of the South Pole is carbon dioxide ice. And so carbon dioxide will freeze out in frost that will almost entirely cover this pole in the fall, and then it will sublimate in the spring. So carbon dioxide on Mars doesn't go through a liquid phase, it goes directly from solid to gas phase. And so this is kind of the two versions, or very simple versions of the carbon cycle that are currently happening on Mars. And as far as we know, because the rate of weathering on Mars is very low, especially in modern conditions, if any carbon dioxide in the past has been fixed into rocks on Mars, that has pretty much stopped that part of the carbon cycle. The erosion needed to kind of get that carbon back into the atmosphere and going through the carbon cycle again, we just don't have those kind of erosion rates on modern Mars. So that's kind of the end fate of that carbon. But for the carbon dioxide that freezes out of the atmosphere in fall and then sublimates again in spring, this is a cycle that happens on a seasonal basis. And depending upon when you image the polar deposits, you can see them either covered in frost or not completely covered in frost. And so we know that carbon dioxide is still cycling through the system in this way on present-day Mars. So now that we've done a lot of review, I am a huge Jeopardy fan, so when Sarah told me to put trivia into this talk, I got really excited. So you can win a prize, but I might enforce Jeopardy rules, which means that you have to wait until I completely finish reading the question. And then the first one to raise their hand after I finish reading the question will get called on by either Sarah or Gotham. And you don't have to answer in the form of a question, but you'll make me the happiest scientist ever if you do. This is basically the first round of Jeopardy, if you've ever seen that. Okay, is everybody ready? Does everybody understand the rules? Okay. So, in what was unlikely to be a case of flatulence, this minor greenhouse gas was detected in small transient amounts by the Curiosity rover.
Whoa! And I saw his hand go up before the
Oh, okay.
But she didn't finish the question.
Oh no!
What is method?
Did he raise his hand ahead of time?
We'll accept it.
Okay. That's correct. What is methane? Okay, so now that we've kind of covered the greenhouse effect and the carbon cycle, next we get to another way of heat, or basically we've talked about the geology and the atmosphere part of Mars and the Earth. Now we're going to talk about how the orbits of those two planets have an effect on their surface temperatures. So this is a quick review of the seasons. And in this case, I'm going to be using the word obliquity a lot for the rest of the talk. So obliquity is basically the measure of how tilted a planet is. So in this figure, the obliquity is 0. The rotational axis of the planet is perpendicular to its orbital plane, which means that the obliquity is 0 and there are no seasons. But as we know in Tucson, there's hot season and hotter season. So one thing you can do to generate seasons then is tilt the planet. So this figure shows the obliquity of about 45 degrees, where the spin axis, which is in red, is offset by some angle from the line that is perpendicular to its orbital axis. So you get some seasons in this case. And this figure shows an obliquity of about 20 degrees, which is in the range of what current Earth and current Mars obliquities are. So current Earth is about 23 degrees, and current Mars is about 25 degrees. So what does this mean for seasons? So basically the tilt of the planet is what's generating the seasons, but the tilt of the planet is not always constant. So this is kind of like a spinning top. If you've ever had a top spin and you notice that it's spinning, but it's also kind of, the bottom of it is moving around in a circle, that's called precession, and that's one thing that can change, or that is due to the changing obliquity of a planet. So in this case, this plot is the Earth, and we have time with present day indicated on the x-axis, and the obliquity is in the y-axis. So the minimum for Earth in this plot is about 22 degrees, and the maximum is about 25 degrees. So this is the variation that the tilt of the Earth has just due to the fact that it's spinning and going through cycles of precession. And so the climate cycle that's caused by this on the Earth is called the Milankovitch cycle, and it's been studied in terms of ice cores and things from previous climates. But Mars undergoes a similar but much more extreme version of this. So this is a similar plot with time on the x-axis and obliquity on the y-axis, except that green bar there, that's the Earth's variation compared to Mars's variation. So Mars goes through very extreme obliquity cycles. One of the reasons why is that Mars doesn't have a large moon like the Earth does in order to stabilize it. And it's also a little bit closer to Jupiter. So some of these variations are actually caused by the perturbation of Jupiter on Mars, which is why Sarah jokingly calls Mars just one really big asteroid. And so due to this, you have changing obliquity of Mars. If you notice, there's some relatively extreme changes. So the obliquity of Mars in this model goes from about 10 degrees, which is possible in the future, to about 45, between 45 and 50 degrees in the past. So this is much more dramatic in terms of changes than the Earth's obliquity. And to give you an idea of the kind of effect this has on the planet, the top plot, which is labeled D, is once again the obliquity plot. So obliquity is on the y-axis and time is on the x-axis, and present day is on the far left. And the plot that's underneath it is the solar insolation. And so insolation is different from what you have in your house. It's actually the amount of energy that the surface is actually getting in watts per meter squared. So as you can tell, the effect of changing obliquity is the change in the total amount of energy that is at the surface of the planet at any particular time. And so this insolation varies from about, maybe it gets up to about 500 here and about 100 here. So that's a factor of 5. And a factor of 3 is all you need on the Earth to make the difference between the poles and the tropics. So this is a potentially major effect on the climate of a planet. So to recap, the Earth has biology interfering with the carbon cycle. And humans are also, of course, re-releasing it, which means this climate system has factors that are not just abiotic in nature. But Mars has the advantage of no humans, trees, or oceans, and no current global scale biology that's altering the climate. So we can kind of remove that biology factor from it this way. And we also know on Mars that carbon dioxide is primarily cycled through the polar deposits. We can see it, like I mentioned before, in the seasonal frosts on the polar deposits, and we can actually see those with orbiting cameras. So where are the ices on modern Mars? Some of them are buried, and I see Dawn in the audience, who also gave a Space Drafts talk, so she has the buried ices covered. I'm going to be talking about the ice we can actually see from orbit. And so the left panel here is the topography for the North Polar deposit of Mars, which is where I've worked most extensively. In orbital images, I haven't actually been there, which is always the fun planetary geology pun to make. And then in the right panel is the South Polar deposits. And so the South Polar deposits is a little bit less symmetric. It also has much more carbon dioxide than the North Polar deposits, which are mostly water ice. But we've basically known since the Viking era that these polar deposits had to have a major contribution of carbon dioxide ice based on stability modeling. So unfortunately in the 70s, a couple of scientists basically destroyed any dream Percival might have had of actually these being giant reservoirs of water that could have potentially fed a civilization. So too bad, it's carbon dioxide. And so the very bottom panel here is a radar image basically showing that there are these discrete packets and layers of the bright lines are basically where you have a major change in material and how permeable that material is to radar. So this is basically a way of being able to see a cross-section of the polar deposits. So we know that there are layers in the polar deposits, which we'll get back to in a little bit. But before then, another trivia question. So a very different Viking landing site, this ice sheet is the closest analog on Earth in terms of volume to the permanent polar deposits on Mars.
What is Greenland?
That's correct. The answer was Greenland. You can give up a nice Viking pun like that.
Good job.
Okay, and so what I mentioned before trivia was that there are these packets of layers within the north and south polar deposits both. In this case, whenever I say MPLD or PLDs, I mean the polar layer deposits. That might slip in a little bit as I get further along in the talk, just because that's how I usually refer to them, so I can say fewer words in my lifetime. So this is an example of an exposure of the North Polar deposits. And so what we can see from this, and this is a high-rise image, is that there are these alternating bands of bright and dark ice. And the difference in brightness is caused by the amount of actual dust in that ice. And so the amount of dust depends on various climatic things going on when that ice was deposited. And it's a little bit harder to see because this is a image and not a digital terrain model is that these scarps are very steep, and the actual thicknesses of these ice layers varies from layer to layer. So the amount of ice and how dusty that ice is kind of what's controlling the overall stratigraphy. And so what's really interesting about this is recording some sort of periodic, potentially, signal in the amount of ice that's deposed on the North Polar deposit over Martian history. So that begs the question, what other somewhat periodic change in Mars's climate do we know of? And that's the one caused by obliquity. So a lot of work has gone into saying, okay, so we have this potentially obliquity-driven climate change, and we also have these layer deposits. Could the obliquity changes be recorded in the layer deposits? And the answer is yes, probably. So there is periodicity in these packets, which is suggesting that there's some sort of signal in there, but pulling out the signal is not as easy as you would think. On the Earth, when you have an ice core, there's rocks and other material that you can radioactively age date within that ice core, but in the polar layer deposits, we don't have any way of doing that. It's a very strong situation of kind of like being in a museum where you can see it, but you can't touch it, and you can't destroy it in order to find out more information about it. So we're kind of stuck. So the things we still don't know are absolute timings. Even if we were able to figure out the relative ages of these layers, depending upon how much ice was deposited, we don't actually have any way of putting that firmly into, okay, this happened 250,000 years ago. Another thing that's challenging is getting absolute accumulation rates. So you can measure the relative thickness of these layers and go, okay, whatever era of climate this layer represents had more ice that was deposited at the North Pole than this previous climate, but it's really hard to tell what the absolute accumulation per year was. And then what the actual present current mass balance of the North Polar deposits is not well known. There's lines of evidence suggesting that it's currently accumulating, and there's lines of evidence that it's currently ablating or having mass removed from it. So there are a lot of unknowns, which is perfect because that means I can answer some of them potentially for my PhD. So what I've been working on is relating current polar conditions, which we can observe the current climate. We have many, many years at this point of orbiting spacecraft observations of Mars and of Mars's climate, including being able to count craters. And we were wondering if we can link this to previous climates preserved in the North Polar layer deposits. And the reason, and this is now my crater counting spiel, is that crater counting is basically a way of being able to tell how old a particular surface has been left out in space. Because little pieces of asteroids or comets or whatever space rocks that are out there are going to be periodically hitting the surface. And if you had a lava flow that cooled yesterday, for example, it's very unlikely that there are going to be very many craters on it because it hasn't had enough time to be out in space to be hit by anything yet. But if you have something that is very, very old, in this case, the heavily cratered areas on Mars, those have been sitting out for a very long time and have had a lot of opportunities for asteroids and other pieces of space rocks to hit them. Which means that if you know the rate at which a planet is hit by asteroids, which you can, in some cases, especially for modern Mars, actually measure, you can get a better idea of how long that surface has been exposed. And so that is going to be able to give us a fixed time for that very top layer, so the current surface of the PLD, which is one of the things we need to know in order to read back that climate history. And there's also, because this is me, a crater, and what's interesting about this crater is that we know, because the area around it is totally defrosted, that that bright deposit inside is not necessarily seasonal CO2 frost. It's probably ice that has accumulated since this crater formed. This crater is about 60 meters in diameter, which means it's very small and most likely very recent. And so this means that, at least in craters, there's ice currently accumulating on the polar deposits. And now that my crater spiel is done, now it's time for 3D glasses. Yay! I think the red goes over your right or left eye, and the blue goes over your right. I always have to look at how to fold the glasses, and I'm like, okay, now I got it. Okay, does everybody have 3D glasses that needs them? Okay. So this is an example of that exposure of the MPLD I was talking about earlier. And so what you can see here is that exposure is on a really steep drop off from the top area, which is taller than the bottom area. And this anaglyph was actually posted on the HiRise public website a couple days ago. So in a shameless pitch for looking at the HiRise website, you can see this data as soon as it's released to the public. So if you have your own pair of 3D glasses, you can go look at these anaglyphs. It's currently North Polar late-ish summer, so a lot of these images are being released. And so the point of this is you see the light layers, you see the dark layers, and they're not all the same thickness. And different exposures of the MPLD have actually been cross-correlated, so we can actually see the same layer in multiple exposures of it. So we're fairly certain that whatever is causing these layers, it's affecting the entire North Pole, which makes sense if it's some sort of large-scale climate process. So on top of these are craters. So this is one of my favorite classic examples of a crater on the MPLD. It's about 200 meters in diameter, which is one of the larger craters. So for reference, many crater catalogs on Mars only go down to 1 kilometer, because that's what previous orbital missions have really had the resolution to do reliably. So HiRise is looking for craters that are on the tens to hundreds of meter scale. And in this case, this crater is relatively fresh. It still has a nice sharp rim that you can really see well in 3D. And it has, doesn't look like it's been filled in by a whole lot, but still at the bottom you can see this bright deposit, and that's most likely ice. And then switching to a slightly larger but probably beaten up more crater. This crater is about 360 meters in diameter, and if you notice, most of the sharp rim is almost completely gone. And what's interesting about this crater is it's the largest one on the MPLD. So the largest crater in the sample size I'm working on is 360 meters, which is about a third of the size of that minimum crater diameter that previous catalogs have actually cataloged to. And it does have this interesting ice mound. So in all of the craters I've showed you so far, there's bright stuff at the bottom, which is probably ice. So whatever's happening in the current climate, ice can be deposited inside these craters. And whether or not that's an effect of the shadowing of the crater rim inside the crater, basically to create a cold trap or not, is literally what I'm working on my next conference abstract about. And then to give you guys some context, this is about a 160 meter polar crater, but this is the kind of terrain that surrounds the craters. Most of the craters are in areas that are relatively flat and have, if you notice especially to the left of this image, this direction, this kind of, I haven't really come up with a good word to describe it, but it's kind of, it looks really a lot like a 10-meter crater, and it's kind of circular. So when updating this crater catalog, it was kind of a pain being like, is that a crater? Oh no, that's just the background terrain of the MPLD. What's also going on here is the dark and light areas are due to dust, and so the dust is currently blowing around the North Pole because it is windy. A lot of the winds are actually caused by the difference in temperature between basically the rest of Mars' atmosphere and how cold the polar deposit is. So those kind of winds are called katabatic winds, and that's mostly what's driving a lot of the movement of dust on the MPLD. So you can also kind of see that there's a wind streak behind this crater as well. If you have really good eyes, you can see there's a bright spot that lies outside of the crater as well as a bright spot in the crater. So something very interesting is going on with the accumulation inside this crater. So the kind of goal of my thesis and the goal of my current work is to be able to take the age we can get from crater counting, the accumulation rate we can get by basically saying, okay, this is how much these craters have filled up, and then control for those shadowing effects like I mentioned earlier, and so that way we can get an age and an accumulation rate, which are the two things we need to kind of look back in time at that trajectory. So unfortunately this is the end of the 3D portion of this talk. But in summary, Mars' climate system is really complicated by life. And so in order to get a good handle on what's happening without biology, Mars is a really good place to look. But the thing is, though, that even though we have the ability to currently observe Mars' current climate, it's really hard to tell what Mars' past climate was like. There's all sorts of conflicting evidence from Mars' climate billions of years ago about how much carbon dioxide could have been in the atmosphere. But a good start is looking at the present behavior of the polar deposits, which is where all those CO2 and other ices are being basically frozen out in winter, with the current climate. So if we can link those two things, that's not necessarily the Rosetta Stone for the entire problem, but it's a good first step. So with that, thank you very much for listening, and I'll take any questions.
Margaret.
So the carbon cycle is part of Mars. There's resident carbon in the atmosphere, and then there's the carbon that's being absorbed into the rock, and then there's the carbon cycle they're talking about. What's the origination of the carbon? Can you extrapolate backwards what carbon ratios in the atmosphere could have been, or would have been, tens or thousands of millions of years ago?
So that's one of the current climate issues on Mars. So for current Mars, we can roughly tell where the carbonates, so the rocks that carry off carbon, are more or less if they've been exposed to the surface, and we can get an idea of how much mass has moved around the poles. The problem with that, though, is that we being planetary scientists, have had a really hard time finding enough carbon dioxide to basically ramp up the atmosphere to levels where you could get flowing water on the surface, which is what all these carved channel images from biking, and so those channels are on very, very old terrains. So the amount of carbon or carbon dioxide in the atmosphere you need to create that, we cannot find a volume equivalent to that currently on Mars. So one explanation is potentially that it's lost a lot of carbon dioxide to space, which is what the MAVEN mission is trying to currently potentially address. So that's more the realm of the atmospheric scientists. But in this case, yeah, we're seeing this discrepancy between the total amount of carbon dioxide we can currently detect on Mars versus what would have been there in the past. So there might be a way of extrapolating it out, but that would require a little bit more knowledge of the MAVEN results, which just aren't in yet.
Follow-up question. Given that the liquid changes so radically, or the incoming flow of radiation changes so radically, is there a sweet spot at some point where there's actually liquid CO2 on Mars at any point, like the last 100 million years or 1 million years?
So liquid carbon dioxide is very hard to get. It pretty much goes right from the solid state to the gas phase. Because another issue in having things liquid means that the pressure has to be good, or in the right space, not just the temperature. So there's a couple of areas of the South Polar deposits where there's a lot of carbon dioxide ice that could potentially bump up the atmosphere from a couple of millibars. But the issue is that's still 1,000 times, so a millibar is 1,000 times smaller than what's currently at the surface of the Earth in terms of atmospheric pressure. So even adding in that, it can't bump the atmospheric pressure up enough in some cases. So it's potential that you could have very brief events of liquid water that for some reason is still liquid due to really high salt content flowing on the surface. But it's a lot harder to actually make work.
What is the length of time of the Mars fall? And what is the length of time, relatively speaking, for Mars spring?
Okay, so the question was, what are the relative lengths of time that Martian fall and Martian spring are? And currently for Mars, they're about the same. Yeah, so 1 Mars year is about 2 Earth years. And actually, I can do this because I've been planning high-res observations for Martian summer, which you have to wait till spring is done for obvious frost reasons. But it ends up being a couple of months, and they're about the same length. One, and it's escaping me right now, is slightly shorter than the other one due to, so Mars's orbit is actually more eccentric than the Earth, so it's more elliptical, but it's not hugely elliptical like a comet. So that does affect the length of seasons. But what ends up happening is the trade-off is the shorter season is when Mars is just a smidgen closer to the sun, and the longer season is when, or longer change in season is when Mars is a little smidgen further away from the sun. So that doesn't really make a huge difference in terms of temperatures. So they're about the same length. One's a little shorter than the other.
Serious question.
Oh, goody. This is going to be a serious question. We'll see if I can answer it.
So I just saw some recent images that had run through, I think, the New Horizons imaging software, and it showed the white spots, but it had some traces of red in those white spots. And I was wondering what the new theory is of what's going on there.
So the most recent published results are that the bright spots at Akhter Crater are salts of some kind, which is not NaCl, like table salt. It's basically whatever can be easily disassociated by water. So it's probably some sort of magnesium salt. What those red spots are, I haven't looked at it in detail, so it could be an image artifact. You might have been looking at an anaglyph potentially. But whatever that is actually currently being looked at in telecom. So the challenge is the composition of Ocrater is relatively well known because it's a huge bright spot, and it's pretty easy to get spectroscopy data from it. But the other issue is that there are other bright spots on Sirius that we haven't had the chance to look at with the spectrometer. So stay tuned for what the bright spots might actually be. But in this case, so far, they turned out to be solved. The question is about learning anything from the residues on Phobos and Deimos, and I haven't looked at those yet. The chances are there's probably some information in there, but the challenge with Phobos and Deimos is we know that they're probably captured asteroids, so whatever their composition is less likely to be what's actually around Mars. I think we're pushing a choo-choo moment here, so I don't know, we'll try to keep asking questions through this until the train is really just here. Might be now. Okay, I can hear again. So, are there any other questions?
With that, one more. Yeah.
Just out of curiosity, a couple of slides ago you showed evidence of on Mars.
Yep.
Do you know roughly how fast those winds are? And so would we be able to notice those winds dancing on Mars at the time?
So that's a little bit outside the area of my expertise because I usually look at the solid stuff and then go like, that's the atmosphere in my model. But they are some of the strongest winds on Mars, and I think you probably would be able to tell. It's not going to be like hurricane level gusts because the atmosphere just isn't thick enough, but they are still pretty significant. And they might be driving a lot of significant erosion. If you notice I should have gone back to the beginning of my talk. Go. There we go, this slide. So you notice how there's this kind of spiral pattern in the troughs around the high topography on the North Polar deposit and on the south one, but not as much. Those are probably carved by winds. So I'm not exactly sure what it would feel like to be standing in those winds, but they're obviously doing some sort of major geologic erosion. Each of these polar deposits are about 1 to 2 kilometers tall, so those winds have removed a significant amount of material since they've been around.
I have one follow-up question to that. So if you were Mark Watney on the poles, would you be stranded due to those winds, do you think? Would it tip over a spacecraft?
So the question was, would Mark Watney's spacecraft be able to actually land upright due to these winds? I'm not sure, but I definitely wouldn't want to be landing at the poles because polar night is coming, and so if winter's coming, I want to get the heck out of there because the sun never rises.
Winter is coming.
Yeah, that's kind of the high-rise. I know the impression I get with using high-rise and looking at the poles is it's like, oh no, winter's coming, I have to get all my images, and then as soon as that happens, it's like, oh, the other pole I can image now because it's daytime, so I usually switch between them. So yeah, so since the North Polar summer's ending, summer will be starting somewhere else.
Okay, let's thank Margaret again. We also have a telescope set up outside if you want to do some stargazing.
Yeah, so they have Jupiter up there, and I looked through it, and it's a really, really clear night here. And I say this as an observational astronomer. You can see the bands of Jupiter through a small telescope, which is pretty darn rare even in Tucson. So go get a look through it. It's really Mars isn't up sadly, but that's there for the night. But it's totally worth seeing tonight. Go out there and give the Student Astronomy Club some love.
Thank you. Yeah, strong work.